So I would like to thank the organizers for the opportunity. I'm very happy to be here and first time in India. And so I'm going to talk about some properties of the Kpz fixed point, although, we still have a lot to learn about the Kpz fixed point. But so I will just put like a small, brief description. I think Daniel will explain you better later. So it's as he was saying, it's a Markov process, taking place on this space of upper semi-continuous functions with some growth control, and that you can describe, through the terminal formulas, the transition probabilities of this Markov process. Okay. So that's the way, so Matejski, Kostel, and Remenick describe it in a recent paper. And so I'm going to be talking about this process. And there are some interesting properties that, as Daniel was telling us, so the first one is this 1, 2, 3 scaling variance of the process. And another one is that it has some, so if you take as your initial profile a Brownian motion, a two-side Brownian motion with diffusion equals 2, then it's invariant for the evolution up to this vertical shift. Okay. So you actually have another invariant measure for this Markov process, but I will focus on this, on this one. And so somehow, if you look locally for the Kpz fixed point, you also have some connections with the Brownian motion, like it does converge locally to Brownian motion. And you can actually prove this by using this type of description of process as a determinantal. And you can prove this kind of convergence in terms of finite dimensional distributions. And using this 1, 2, 3 scaling, you can actually connect the local behavior of the Kpz fixed point with the long-time behavior of the Kpz fixed point. Okay? So essentially from this result, you can also get that if the initial data is convergence in distribution, something in UC, then you have that the evolution of the process goes to two-side Brownian motion. Okay? So this is what I mean by ergodicity of the process. And so they were also able to prove this result in terms of finite dimensional distributions, again using this determinantal description of the process. Okay? And so there is another interesting property that is related to what we call this variational formula for the Markov process. And so to write down this variational formula, you need to define this object here, which we call the Ayyer sheet. And so uniqueness is still, in their paper it was kind of open, but it seems that now it's been solved by some other authors as well. And so the point is that if you define this process as a process of Z and X, okay, and then you can write down the evolution of the Markov process in terms of a variational formula. So you have your initial data here, and then you sum this Ayyer sheet, and then you subtract a parabola. Okay? So in this way, it's a very natural way to define, also to construct your process, because it's a way that you can take two initial different profiles and then evolve them with the same Ayyer sheet. So in some sense, this is a kind of a natural way to construct a coupling for your process. Okay? A basic coupling, let's say. You start with H0 and some other H0, and then you run them both together. Okay? So So this is what I just wrote here. So what I'm going to do here is I'm just going to define the process starting from some initial profile at 0, and then start it with the two-side Brownian motion with coefficient, diffusion coefficient equals 2. Okay? And the question is, can we get ergodicity from this type of variational formula? Okay, can we get this convergence by looking at this kind of formulation for your process? Okay, so do they get close together as time goes within? That's the type of question that I'm interested in. And so what I want to show you is that it's actually possible to get like somehow a strong result. Okay. So here, this is just the uniform norm. Okay. And so if you assume a similar condition on the initial data, and so you look at the probability that they will deviate as eta times square root of a, then you can get like a good upper bound on this kind of probability. So theta is just some function which goes to 0 as delta goes to 0. And here we have also some other term which depends on eta. I put this term separated just because this guy doesn't depend on eta and that guy depends on eta. So, and as a corollary of this theorem, you have that it does converge in probability to 0 as time goes to infinite in a strong way. Okay, not only in finite dimensional distributions, but in a subnorm. Okay? And the point is that, so the way we're gonna to prove this result does not really use any of this kind of property, this kind of determinant of structure of your process. Okay? And the point is that, so there's a lot of things, that actually there are a lot of tools that you can use to, study this kind of process, and mainly you can classify them as, some of them are belong to this kind of integrable world, and some others belong to what we call the coupling method world. And what I'm going to do is to explain more or less how you can use this type of coupling argument to get this kind of property for the Kpz fixed point. Okay? So just a remark, because I have this version of the proof of this theorem, which is so the proof that is written there just for initial profile that satisfies this condition. And here it's a little bit more general because you just have to converge. And so in an upcoming version, I will just put the extended proof for when this is convergence. Okay. So let me just review what Daniel told you this morning. You can see this Kpz fixed point as the limiting object when you look at the fluctuations of the totally asymmetrically simple exclusion process. Okay, so he has already given a nice description of this process. So I will be you have particles jumping to the right at rate 1, subject to the exclusion rule. So particles cannot occupy the same site. So if they try to jump to a site that is already occupied, so the jump is not allowed. So you have these particles going right. And from this particle configuration, you can construct a growth model, as he was describing. So here, I'm considering the growth model going upwards, not downwards, okay? It's just a matter of convention. It doesn't really matter. And so you can actually write down what is the formula for this growth model. And by just taking the number of particles that jump from site 0 to site 1, 0 times 0 interval 0t, and then So at 0, you put this value, and at the other points, you just put this value plus some according to if the particle goes up or down. You see here, it's up or down, if you have a particle or if you have not a particle. Okay? And the dynamics, as we saw, is just the local minimum becomes local maximum with rate 1. So I'm going upwards here. Okay? And this is some picture. So this hand simulation, and this is a true simulation that I took from Patrick's website. So here, so you start with the step initial profile, this narrow edge type of profile. And so as time goes, this is the macroscopic shape, and then you have these fluctuations of the interface. And you also have this flat initial profile. And you also have this macroscopic, and then the fluctuations. Okay? And so what, so to get the Kpz fixed point, so we are going to scale in a window of size n to the 2/3 n to 1/3 to see non-trivial object. And so I'm just rewriting down the theorem from Matthäus, Costel, and Remenick. So here I just wrote it a little bit different. So my epsilon here is the n to the minus 2/3, my epsilon. Okay, so he wrote it in terms of epsilon, I'm writing it in terms of n. Okay, and so this gives you the convergence of the TASEP growth model to this Kpz fixed point, as he was saying. So, and so this for us will be this will be important for me because I'm still not able to use the coupling method directly in the, let's say, Kpz fixed point world. I will need to somehow construct the coupling in the discrete scenario and then take the limits. I wish I could do this directly in the Kpz world somehow, but still not possible. Okay? I think it will be possible at some time. But, so I'm going to use this kind of result to construct the proof of the theorem. So this is just an example, like some examples that Daniel was telling you. This narrow edge, the flat, and the stationary condition. And so this is also, so we allow that the initial profile part depends on n, so that you can always reconstruct any function from UC from your initial profile. Okay. So so to develop this the coupling method, I will rather work with a little bit different object. So I will not be working with actually the height function, but I will be working with the times where points become occupied. Okay. So let me describe what I mean by this. So instead of considering this growth model, so I will just rewrite it in a different way, but you will see that it's just the same description. So I will start with an initial profile, okay, that I can construct from the particle configuration. Okay? And this is, let's say, a picture of it. So you just take the picture that we were like this and then translate it like 45, you rotate it like 45 degrees. Okay? And then, so the evolution is that, so you have, so I will say that these are the occupied sites, and at that side you have like sites that are free, and they will become occupied at height 1, okay? As soon as K-1L and KL-1 are both occupied. So every site that is in a corner, like, so this one here you have corner, so it will become occupied at height 1, this one 2, this one 2, this one 2, this one 2, and so on. So you see that it's just similar description because you can see these corners as local minima that become local maxima at rate 1. Okay? And so I will define also what we call the last passage time associated to this corner growth model, so as the time when KL becomes occupied. Okay, so I can describe these corner growth models in terms of the times where the sites become occupied. Okay. And of course, there is this nice connection between the evolution of the height profile and the times when sites become occupied. And through this connection between these two objects, so since you have like a theorem telling you what is the limit fluctuations of the height functions, using this connection, you can also get the limit fluctuations of last passage times. Okay? And so if you define this, so you asymptotically, this time will be like 4Tn. And so if you subtract it and divide it in the 1, 2, 3 scale, then you also get the same object as Daniel was explaining you, the Kpz fixed point. And so I'm going to actually use this last passage percolation times to construct the coupling in all the arguments for to study the, you know, the how long, you know, to study the deviations from initial arbitrary profile from the, let's say, the stationary one. Okay. So there's some things here that, so it's somehow it's from this formula here is kind of direct to see that you have finite dimensional convergence of this age for the last passage times. And you can also actually show tightness and get the functional convergence in the space of continuous functions. And so you have like this stronger statement here. And so there are a lot of interesting properties related to this last passage times that I'm going to use to construct the coupling. And so the first one is that they satisfy this recurrence relation, okay? Which is pretty simple because, so the rule is that, so site KL will become occupied as soon as site K minus 1L and KL minus 1 are occupied. So the time it will be occupied is just, I will take the maximum because I need both of them to be occupied. And then I will just wait exponential random variable parameter 1 to become occupied. But you can integrate this relation backwards, okay, to actually have this description of last passage percolation time, just this occupation times, in terms of maximization of sums of times along upright paths, okay? So if you define this L, what I call L as from X to Y, okay, by the maximum over all possible sums running over all possible upright paths from X to Y, then this variable also satisfies the same type of recurrence. So this is what I mean by an upright path from X to Y. Okay. So this is another example. And you can also, so here I'm defining the point-to-point, what we call the point-to-point last passage percolation times. And we can also define the curve 2-point last passage percolation times. I'm just explaining this picture. So I want to define the last passage time from this curve, from this initial profile to Y. So what I'm going to do, so I fix Y, I'm going to see all the corners here that I can go from this corner to Y. So I have all this, for this example, I can reach Y from this profile from here, from there. And so from here I have all these upright paths, from here I also have all these upright paths, so they just maximize of all possible upright paths from these 2 points to Y. Okay, so it's a well-defined object, it's a finite number of them, you take the maximum. Okay, and then you can see that you can recover the point-to-point last passage time by looking at the curve to point with initial profile like that. So which corresponds in the Kpz fixed point world corresponds to the narrow wedge initial profile. And you, of course, you also have the flat one. This is not the flat one, but you can just get the flat one like this, and so on. And so to construct this, so the argument, I'll say, the proof of the convergence of probability. So I will work on this LPP model, but with slightly different construction. And so let me describe it here. So what I'm going to do is I'm going, instead of considering a curve to point last passage model, okay, I'm going to fix. So I'm going to fix the boundary, and I'm going to put values at the boundary, okay? So this B here, for me, represents times that I will attach at the boundary of this set here. So it's just the coordinate, the positive coordinate axis, okay? I will attach these values at this boundary. And so I will have these values, and I will construct a new environment. So you think that you have these exponentials, random variables of parameter 1 in Z2 plus. And along the boundary, I will attach the values given by this B. Okay? So you have values along the boundary, and in the bulk, you have exponentials with parameter 1. So here I have the values that are given by this boundary condition, and inside I have just exponentials with parameter 1. Okay? So that's the definition, precise definition. And so along the boundary, I will just sum, the values. And I will define this new last passage percolation time as the maximum that I can get by summing the value along the boundary and then going to X through the bulk. Okay? So this is just a representation of that. So if I want to see what is the last passage time in this model from 0 to this point here, let's say X, I will maximize over all possible passes. So I just sum the weights along this boundary, and then here I just have the exponentials with parameter 1. Okay? Then I maximize over all possible paths. So you can just write down this as and this is nice because you see that this description looks very much like the first one I was writing now for the Kpz fixed point. So here you have like a maximization of something, what you can see as like your initial profile, and then you have some other thing that we will see is related to this Ayyer sheet in Kpz. Okay? So I will use this description. Okay? And so the nice thing about this model is that you can recover the previous last passage model by just putting, by just putting as your boundary condition the times that you get from the curve to the positive coordinate axis. Okay? Just define your boundary. So giving your initial profile, you just define the boundary values like this, and then you have this equality. So I put just the boundary here, so I have my initial curve here, and then I just define the times here just by subtracting the time from here and to the time from there. Okay? So I have this. So in this model, I can recover the original one. And I also have what we call the stationary model for this LPP model, which is that if I put exponentials with parameter 1 minus rho on the horizontal positive x and exponentials with parameter rho along the vertical positive x, then I have this kind of stationary property. So let me write down, because I will use it later. So I'm going to do a picture here. So here I have exponential with parameter 1 minus rho Here I have explanation with parameter rho, and here I have explanations with parameter 1. And if I look at along the anti-diagonal, you see this is, so that also means, right, yes. So Kn for me is, I'm looking at points along the diagonal. Okay. So if I take so this increments here along the diagonal, then I have a very nice description of the distribution. Okay. If I subtract the last passage from Kn and the last passage from K minus 1n, then I have a collection of IID random variables with this distribution, which is given by a difference of 2 explanations with parameter 1 minus rho and rho. Okay? So this zeta nk rho will be just equal to explanation 1 minus rho minus explanation with parameter rho, and they will be I. Okay. So in order to get this, so let me just write down here. So the question here is, I want to control the probability that, so I'm looking at the subnorm of, so the Kpz fixed point minus, let's say the Kpz starting from a Brownian motion in an interval of size A, okay? So this is the subnorm of minus A of, the functions here. And I want to see, what is the probability that this is bigger than eta square root of A. So what I'm going to do is I will, so this is the continuous model. And so before studying this, what I'm going to do, I will study the discretized version of that. Okay? And then I will just compare, let's say I start with some initial profile here. I define just the boundary, which corresponds to this initial profile. Then I just couple it with this model, and then see how this evolves. Okay? That's the idea. And of course, when I do the scaling of this model, I get for free Brownian motion. Okay? Just like Donskoy's theorem. And when I rescale the curve to point, I will get the Kpz fixed point. Okay? So this just standard result that you, so from this, if you take the stationary one, so along the anti-diagonal, you just sum IID random variables. So if you take this delta rho nt, okay, and just do the limit as n goes to infinity, you get like a standard two-sided Brownian motion for all t bigger than t. Okay? So I will define the same object, so but not not only for the stationary one. I will just start with the initial profile h, and then define this delta h. Okay, I'm just looking at so the difference in x and to the third minus the last passage at 0. Okay, so of course you have this relation between the delta and the previous big H. So the big H is, I'm looking at the fluctuations of the last passage times, so which we know goes to the Kpz fixed point. So of course you have this relation, so saying that, so if I look at the fluctuations at x, so it's just so I do a vertical shift over delta, okay? And so since we have convergence of H, of big H and Tx to the Kpz fixed point, so we can just translate this delta in terms of the delta associated to the Kpz fixed point. Okay, so they are just equal up to some multiplicative constants. Is that clear? Okay. Here, I'm not using really the, so remember that for H you have, so for H you have this constant C1 here, say 2 to the 4 to the third, and you multiply X by 2 to the third, and here for my, so this delta here, I don't multiply X and I just divide by the variance of this random variance when you take rho equals to 1/2. And what you get is so sigma is 2 to the third over 2. Sigma squared is going to be 8, so you get just bigger. Okay? So what I'm going to do now is, so if I want to control, this probability here, oh, sorry, there's this delta here, okay? Just remind you what is the delta. You just, okay. So instead of studying this guy here, we just study this delta TH0. And delta T 1/2 for me is just a standard Brownian motion with sigma equals 1. Okay? So then as I was explaining, so in this LPP, you have a very natural coupling, which is a basic coupling. So you just take different values along the boundary. Just take B1 and B2, and then here on the bulk, you have the same exponentials with parameter 1. So this is fine, a natural coupling. And that's the coupling we are going to use here. And so to make it work, so in order to be able to control this kind of behavior, we're going to use two basic properties of relates to this coupling. And the first one is what we call the local comparison. And it says that, so let me explain to you a little bit what is the Z. So the Z is, so remember that for the last passage model with boundary, so I have LPP with boundary. So I have this maximization that I go along the boundary, I pick up the weights along the boundary, and then I go to point X, pick up in the weights in the bulk. And so you will have like one maximal path. And then Z is exactly the point where it leaves the coordinate X. Okay? Is exactly the argument in this Z where you have the maximum. So we might not have one, so you just take the maximum one. Just, you know, the rightest one, okay? Rightmost one, okay? And this local comparison property says that if you are able to control, if you have some, so if the exit points are ordered, then the increments are also ordered. Okay? So that's the first property. And the second one is what we call attractiveness, is that if you start with two profiles that are ordered in terms of the increments along the boundary, then the last passage times also remain ordered. Okay? And here I'm just take the increments along the boundary. Okay? So I'm not going to prove these two lemmas. They are kind of basic properties. But I'm going to use it strongly to get upper bounds, now useful upper bounds for this probability. Okay? And so the idea is that I'm going to somehow try to sandwich. So I will take the LH, which I want to compare with the Brownian motion, and I'm going to try to sandwich it between two Brownian motions. Okay? But I cannot take the Brownian motion with the traditional Brownian motion because this will not be true with high probability. But if I kind of slightly increase 1/2 to something, then you might have that with high probability. And if I decrease 1/2 a little bit, you might also have the other inequality with high probability. So, and that's what I'm going to do in order to get the to control this type of event. Okay. So what I mean by increasing 1/2, I will just take 1/2 plus or minus some value r of t, so times t n to the power minus 1/3. Okay. And we will see how it works. Okay. So this is actually the most important result. Somehow it's the lemma which makes everything to work fine. And so I call this the Kpz localization. And so I will just briefly describe it as a picture here, okay? So En for me is so let me draw a picture of this event En here. So remember that you have, so I will be always work with, so I have this, so I have the boundary with parameter rho minus, I will have the boundary with parameter rho plus, I have the boundary with your initial age, okay? And I will also have the boundary with parameter 1/2, everybody coupled together, okay? So, so the event is that, so I will have these two positions here, minus Tn essentially to the third, so Tn to the third. So it's not really Tn there, it's An, but so let's just think this is An, okay? And so I'll take the maximal path here and see where it lives for Z minus rho plus, and also for, so this is my ZH minus. So this minus here means that it comes from minus Tn to the third, and the minus here, it comes from minus Tn to the third. And I also, so I want that this guy is to the left of that guy. And so I want a similar thing here. So I will have this Z plus of H here, and I will have the, let's say, Z plus of rho minus. So what I want in En is that actually is essentially that the exit points associated to profile H are in between the exit points associated to profile rho minus and rho plus. Because at the end, what I want to do is actually to bound the increments corresponding to H by the increments corresponding to rho minus and rho plus. Okay? So you can, so this event, En, is actually the event where the coupling gives me good bounds, okay? And so what I'm going to show you is that this event has actually high probability, okay? And that actually corresponds to this function theta, which appears in the upper bound of this probability, okay? So let me just try to describe to you the proof of this lemma, because it's just the central lemma in the whole.
Is the fact that the sandwiching things are stationary?
Mm-hmm.
They could be anything.
No. I will use it. It's stationary. Because after I want to take the scaling limit.
No, but I mean for this lemma. You write the same lemma for any
No, because I need good controls on the, because, so the strategy to show this lemma is, I know where this guy will be somehow, and I know where this guy will be as well, and I know where this guy will be too. So if I know their positions, then I can tell you if this will happen with high probability or not. Okay? Try to explain you. It's just a sketch of how does it work. So I will just write it a little bit different. So we call that we have this delta t, which is a t to the minus 2/3, and I will call RT is my delta t to some power minus alpha. So I will choose alpha 1,4 afterwards, okay? But just let's work with some alpha there, and then you will see why. You actually have some freedom to choose this power. So instead of looking at position an to the 2/3 minus an, I would just think that a equals 0, okay? Just to understand how does it work. So if we take like a equals to 0, which doesn't really make sense here, but okay, let's think that instead of looking at this position, you're looking at this position and you want to control the exit points, okay? So what happens with this z h n of 0Tn, okay? So you can just write it as an argmax, okay, of, so what you can pick from your initial profile, okay, plus, so let's write it as like Hn plus the Lz from 0 to nt. Okay, this is the definition of my z. And so you can just rewrite that, so you just do some rescale. So you can actually write zhn 0Tn divide by some constant, let's say C1 to the 2/3. You can just write this as argmax, but now, so just call it omega of nt, okay? So this is just the argmax over omega. And now I will just rescale it in the Kpz 1, 2, 3 scaling. So omega n to the 2/3 divided by n to the 1/3. That's some constant here, which is not really important. So from L to omega n to the 2/3, 0 and t divided by some other constant, the same constant actually, minus 4n. Okay? You just have this description here. And when you do the limit, what happens? So when you do the limit, so this guy here will go to something like the argmax of H0 of your omega, which is your initial profile, okay? Plus the limit of this object here, okay? And the limit of this object here is given exactly by the Ayyer process minus a parabola. So what you get here is a t to the 1/3 times the Ayyer at t to the minus 2/3 omega minus omega squared over t. Okay? So, but still we have some dependence on n, on t, sorry. So how can I understand the dependence on t? I will do just rescale again, okay? And I will call u equals to t to the minus 2/3 omega to get that omega t divided by t to the 2/3 equals to this new ut, okay, which I can describe as the argmax over u of t to the minus 1/3 h0 u to the 2/3 here plus a of u minus u squared. Okay? So I get rid of the t in the Ayyer process and in the parabola by doing this rescaling. Is that clear? Because you see, so the t to the 1/3, I can just rewrite this. I can put a t to the 1/3 here times omega times t to the minus 2/3 squared. Okay? So I have a t to the 1/3 here, I have a t to the 1/3 here. I can just take the t to the 1/3 out by just putting a t to the minus 1/3 here. And it will not change the argmax. Just a multiplication. Okay? And then when I put u equals to t to the minus 2/3 omega, here what I got is u, and here's this. Okay? So now we see the condition here. That is, if I write epsilon minus 1 to be t to the 2/3, so this is exactly epsilon minus 1/2 h0 of epsilon minus 1. Yeah. Okay? And if this guy converges to some h of u, okay, what you would expect, that this guy here, as t goes to infinity, converges to some random variable, u, given by the argmax over u of this hu plus a of u minus g squared. Okay? So somehow, what I have is that this zhn 0 tn is approximately distribution something like u times n to the 2/3 times t to the 2/3. Okay? So I can give you a description of where is it going to be somehow, z. So now I have to do the same for 0 plus and 0 minus. So I will not explain in full details, but somehow from the work of Balash, Kator, and Sepalen, they have a very good description of this 0, and also using coupling methods. And they can actually show that if you choose rho nt equals to 1/2 plus or minus RT divided by nt to the 1/3, then this z rho plus minus nt, sorry, here's nt. This guy will be close to plus or minus RT times n to the 2/3 t to the 2/3. Okay? And now see, here I have a random variable, u, which doesn't depend on t, sorry. And here I have RT, which depends on t. Okay? And if, for instance, if I fix a and send t to infinity, this RT will become larger and larger. Or if I take delta small, RT is also larger. Okay? So here you can see why ENT has high probability. Because this guy, so the plus is following RT plus, the minus is following RT minus, and the middle one is just some fixed random variable, u. So with high probability, ENT will occur. Okay? So then, so what I have to do now is to, so as I told you, so I have these three boundary conditions, 1/2 plus something, 1/2 minus something. I will couple them in another way. So I just start with 1/2, and then I make a transformation, simple transformation of exponential random variables in order to get, here I will get, so with plus I will get a whole plus, and with minus I will get a whole minus boundary. And so you just can check that they satisfy this, in this coupling here, they just satisfy this order. And so you just see that on the event AN, I can just bound the delta associated to the profile H by the delta associated to rho plus and rho minus uniformly on the interval A and minus A. It holds for all x in this interval. And by attractiveness, you have the same for the 1/2 profile. So you have that these two guys are sandwiched by this delta plus and delta minus. Okay? So the difference between them, I can just upper bound this by the difference between delta plus and delta minus. Okay? And by attractiveness, again, the difference between delta plus and delta minus is an increasing function. For instance, if x is on 0a, this will be an increasing function of x. So I can just bound this guy here by the value at a. And a similar thing I can do for the negative part, the minus part. And I can just bound it as at the value at minus a. So I have a uniform control here. So what this shows that these increments here in the discrete level are bounded by a very nice random variable. Because what is this ENT here? So here I have this bound, so what I do is just Chebyshev. So, okay? I just split this probability in ENT and ENT complement. So here I have ENT complement, and then the other part I just apply Chebyshev. Okay, this ENT is positive, I can do it. And so what is left is just to bound the expected value of INT, okay? And so it's not really, it's just using the definition of rho plus and rho minus. You just make some simple calculations to see that this ENT is just bound by some universal constant, say, I think it's 22 bits there, by square root of a, and then you have delta. So if you take delta t equals, if you take RT delta t to minus half, what you get is delta t 1/2 minus alpha. So if you choose alpha equals to 1/4, then you get delta t to the power 1/2. Okay? But you could have choose some other alpha, but I think it's nice with 1/2. And that's all. Because you have this limit, you know how to control this probability, you know how to control this guy here. So you have that this guy converges in a strong sense to the Kpz fixed point, this guy converges in a strong sense to the one start from the Brownian motion. So you take the limits, you get the theorem. And that's all. It's somehow simple as soon as you realize how to use this coupling to get the bounds on the difference. Okay? So I'm sorry for taking a few more minutes of you, but okay, I'll stop here. Thank you very much.
Questions?
Yeah, so the first term is this delta, this theta of delta. So essentially when you want to bound the probability of E and T, so what you want to control is what is essentially the probability of this. roughly, okay? Because you have n to the 2/3 and t to the 2/3 in both sides, so if you want to see what is the probability of nt, essentially what you get is this. Okay? So everybody somehow would agree that this guy has a very nice tail behavior. So some people think it's, so if you put an L here, minus L here, this should be a further exponential of minus, I think it's L to the cube, yeah. So that's what you should get, is this delta t, this theta. So this theta should be somehow related to this function here. So it's a very strong bound. The second one is not so strong, but I don't know if we can somehow try to improve this other bound here, but I'm not so sure. Yeah.
Any other questions? Other questions? All right, if not, let's thank Leandro again.
Thank you.